In this video, we will discuss the definition of the Laplace transform. For a function f defined for positive inputs of t, we define the Laplace transform of f of t to be this improper integral from 0 to infinity of e to the minus st times f of t. That is, whatever function we would like to find the Laplace transform of, we need to substitute in, evaluate this improper integral. Now, of course, as we've seen, when you evaluate this integral with respect to t, what remains is the variable s. So the notation we typically will use is a capital F of s to represent the Laplace transform of a function lowercase f of t. And because of how the Laplace transform is defined as an integral, there are several properties of integration that we get for free. Namely, the fact that the Laplace transform can be broken up over addition, subtraction, and constants can be pulled out front. That is to say, the Laplace transform of a times f of t plus b times g of t can be broken up as a Laplace transforms of f plus b Laplace transforms of g. And when it comes to evaluating Laplace transforms, there are two types of questions we could expect to see. The first of which is to use the definition to determine a Laplace transform. So for example, let's use the Laplace transform to find the Laplace transform of 3 times t, just as a simple illustration of how we go about this. So using the definition, that means we must go back to this improper integral. So that would be the integral from 0 to infinity e to the minus st times 3t. And whenever we are asked to use the definition, then you must evaluate as this improper integral. So the first step is to write this as a limit, and then we will integrate. And in this case, what we are integrating is a polynomial multiplied by an exponential. So the desired method of integration in this case would be by parts. So as we've seen with many of these examples, we will let u be 3t and dv be equal to e to the minus 3t. Then du is 3 dt and v is minus 1 over s e to the minus st. And integration by parts tells us we multiply together uv. And note, at each step we're going to write an equal sign and have this limit until we evaluate it. So uv is 3t, and I'm going to put a minus over s, e to the minus st. And this is evaluated from t equals 0 to t equals b. Then we subtract away the integral of v du. So we'd be subtracting away the integral from 0 to b of minus 3 over s, which is a constant. We can pull that out front. Minus a minus becomes a plus. And we need to integrate e to the minus st one more time. So cutting and pasting down here, I'm going to go ahead and take care of evaluating this first term. Make each t a b, minus sign, replace each t with a 0. So minus 3b over s, e to the minus sb. When we substitute in 0 for t, we simply get back a 0. The antiderivative of e to the minus st is minus 1 over s, e to the minus st. So that's a minus 3 over s squared, e to the minus st. And then once again, we need to take care of evaluating from 0 to b. So at each step, we keep writing this limit until we have evaluated it. So t equals b would give us a 3 over s squared e to the minus sb. We subtract away what we get when we substitute in t equals 0, but we're very careful to make sure we account for that negative sign out front as well. So it's minus a minus 3 over s squared. And now we are to the final step. So as we've observed multiple times in class, as b goes to infinity, this middle term will approach 0. And I'm going to put kind of just a small kind of asterisk here to indicate that this is true as long as s is a positive quantity. Similarly, this first term will go to 0. And note, because there's this b e to the minus sb, we don't need to do any work or really provide any justification, but that follows from L'Hopital's rule. And what we end up getting is just that 3s squared left over because it is a constant with respect to b. And this is an example illustrating how we can use the definition of the Laplace transform to find the Laplace transform of some given function. The other type of problem we can be asked related to finding a Laplace transform would be using our common table of Laplace transforms. And some of the common Laplace transforms we see in 7.1 are listed above. These should be the things that after you've practiced for a while are almost second nature. Even though we'll have a formula sheet on the exam, you don't want to have to waste too much time looking up these formulas that you should just know. Now, using properties of the Laplace transform, this final example can be very quick and very simple. We break it up, we pull out constants. So 2 Laplace transforms of sine of 3t plus the Laplace transform of e to the minus t. And now note, each of these 2 remaining Laplace transforms follows very quickly from our table. The Laplace transform of sine of 3t, that is the sine of at formula, where a is equal to 3. So this would be 2 times a over s squared plus a squared. And for e to the minus t, that corresponds to the e to the at formula there, with a being equal to minus 1. So this would be 1 over s minus a minus 1. And of course, I'd probably rewrite this just once here as 6 over s squared plus 9 plus 1 over s plus 1.